Assalamu alaikum wa rahmatullahi wa barakatuh. This is Dr. Ali El-Moursy, and we are giving the lecture or recording the lecture for Digital Logic Design, DLD, lecture number 23, part 1. 23, part 1. We are starting now chapter number 5. We are starting chapter number 5. In chapter number 5, we need to do a kind of extensive shifting to our thinking. Till chapter number 4, we build what we call the combinational logic circuits. As we have demonstrated in the circuits that we have built in chapter number 4, in particularly the adder, the subtractor, the comparator, each time the number of inputs that you want to add, which actually reflects on how complex you want to build your circuit through, you have to add extra hardware, extra logic. Like what? Like the examples that we have given in adder subtractor. If I want, instead of adding 4 bits to 4 bits as we demonstrated in the adder subtractor, if I need to add, yes, the expansion is easy because actually you want to add more full adders. However, the hardware for the processing should be added in order to do the processing for larger numbers. And similarly, if you want to do this processing for more complex operations or for more complex numbers. If I give you an example, a simple example, like multiply 2 by 3, you can give me the answer right away. The answer is 6. But if I give you a complex mathematical operation, you will start to think. Like for instance, if I want to multiply number in hundreds, maybe 256 multiplied by 1,200, something like that. Okay. For this complex operation, you cannot do the processing, even as a human being with a very sophisticated brain. You cannot perform the operation right away. You cannot just give me the answer. But you still can do the operation. What will come to your brain, to your mind, once I give you this complex operation, you will start by thinking, okay, what to do. The first thing that will come to your mind, if I give you this complex operation, I ask you to do it, is that you will start by writing the numbers down. 256 multiplied by 1,000, maybe 306, whatever. So the first thing that you come to your mind is to write the numbers down. This is just put here. We are in lecture 23, chapter 5. Motivation for synchronous, for the sequential circuits. For the sequential circuits. This is our title of the lecture. Going back to our example. So the first thing that you did, in order, when I give you this complex multiply operation, okay, is that you will start by writing down the numbers, and then you will go into a process for the multiplication. We usually put the numbers like this. We have some protocol or mechanism, and we will start doing what? The multiplication step by step. First, you will multiply 6 multiplied by 6. So you will get 6 by 6 is 36. So you will have 6 and 3. Then you will multiply 6 by 0. So you will get 3. Then multiplying 6 by 3. You will get 6 by 3 is 18. 8 and you have 1. 6 by 6. 6 by 1 is 6 and 1 means 7. And so on. So you will go and multiply this by the number, multiply this by the number, making addition, and you will get the answer. So for the complex operations, what the lesson that we want to learn out of this example? For complex operations, I cannot perform the operation at once. As an opposite technique is that I actually do the process sequentially. That means I will involve myself into a sequence of steps. Each of them is a simple operation by itself, so my brain can do it. So I will involve myself into those sequence of steps. First of all, I dissect the complex problem into smaller, simple steps. This is one thing. The other thing is that I need to have a memory. And the first thing, the first characteristic, let's write here the characteristics of sequential processing or sequential circuits. The first characteristic is that I need to have a memory. I want something to store the numbers that I have. The system should have a memory. Characteristic number 1. The characteristic number 2, that I do not do the operation at once, but I go into sequence of steps. So the result that I get is an intermediate result. This is not the final answer. This is just part of the multiplication. I have to continue in the steps of the multiplication, and I have to accumulate the numbers here to get the answer. Correct? So here the operation is time dependent. The output of the system will change over the time until I reach the final correct answer. The operation is time dependent. It has a memory, it is time dependent, and the last characteristic is that I'm producing some answer, okay, which is an intermediate answer. This is not the final. So later on, after I do the rest of the multiplication, if I perform this 5 multiplied by 6 is 0, 30. Okay, so that means this is 30. 5 multiplied by 3 is 15. 5 and 1. 5 and 1 here is 6. Okay, then I will multiply also the 2. 2 by 6 is 12. 2 and 1. Okay, 2 multiplied by 3 is 6. 2 multiplied by 1 is 2. So the answers that I get here are not final. I will enter those results back into my system to add them together. to get my final answer. Okay, so I have the 6, then I will add the 3, I will add those together, which will give me 3 and 1. 1 here means 13 and 1, 1, and this is 3 and 1, and this is 3. Okay, very funny number. Anyway, this is my answer. So the system should have a memory. The system is time dependent. That means the output of the system will change over the time. I don't get the final answer at once. I get an intermediate answer, and then I get another value, and so on. And the last and the most important characteristic of these systems is that the answer that I will get, I will involve it back into an operation to get a partial answer, and then I will involve it back to get the answer. So the system, so the output of the system is connected back as an input for the system in order to get the following outputs of the system. We call this a feedback. So the system should have a feedback. System should have a feedback means the output of the system is fed back to the system as an input to produce the new output, and I will keep doing this until I reach my final answer. Okay? So this is actually what characterizes the new systems or the new circuits that we are learning, which are called the sequential circuits. Sequential circuits. Sequential circuits are digital logic design circuits, but they have to satisfy 3 conditions that actually allow those kind of circuits to perform operations, complex operations, hard operations, or operations performed on long numbers that was not being able to achieve easily in the combinational circuits. This is the main difference between sequential circuits and the combinational circuits. 3 characteristics added here. The system should have a memory. The system has a feedback. The system is time dependent. Means the output of the system at any given time depends on the previous output of the system, and it's connected to the feedback too. So the output of the system is also an input for the same system to produce the new stage of the new value of the system, which makes those circuits difficult, tough. Because right now, this feedback and this time dependency of the system make the system not that easy to understand or to analyze, also to design. However, we will, through this chapter, will actually indicate and demonstrate very simple steps in order to design, analyze the circuits, the sequential circuits, the digital DLD sequential circuits. Okay? To motivate you more about that, I will show you a ready-made circuit that we have built similar one to that circuit in chapter number 4. Okay? We will show a paradigm shift in designing the circuit, and we will discuss how this new circuit is different from what we have designed before, how it utilizes the sequential circuit design properties and characteristics, and how this benefits us in order to achieve a much better circuit. Let's go. It's also part of the motivation for this. Here I am discussing what's called serial adder. The circuit name is serial adder. Watch this interesting design. Can you see this circuit that we have just drawn? What's this circuit? The components of this circuit are not new for you. At least one of them you can recognize in the circuit that I just drawn here. This block. This is actually the brain of this circuit. The circuit is called serial adder. Okay? And this is actually a 4-bit serial adder. This circuit replaced the circuit, the 4-bit adder that we have built in chapter 4. Do you still remember the circuit in chapter 4? In chapter 4, we have used 4 full adders connected back to back cascadedly in order to add 2 numbers of A and B. Right now, we changed the design significantly. You can recognize in the circuit here, you can recognize actually 4 or 3 main differences. First of all, I used just a very significantly smaller circuit. Here, instead of using 4 full adders to perform the 4-bit addition, I only used 1 full adder. But the full adder alone is not enough here. I have to use also those 3 guys, those 3 small arrays that we have seen. Those actually are called shift registers. What are shift registers? Those are just storage. So if you wanted to add the number A and the number B together, and each A and B are of 4 bits, so you have to store first the values of A0, A1, A2, A3, and so do for B in the registers. You can also see another register here, and this is to produce and store the output that will be produced by the circuit. Actually, the registers are storage or memory. Storage is memory, and memory is a storage in our definition. This is the first difference. System should have a memory. Second thing, system has the last third condition, should have a feedback. You can see here the output from the full adder, the C out, okay, is connected back to the C in. So the system has a feedback. The third thing we need to demonstrate it. The output of the system is dependent on time. And through the feedback, the output of the system at any given time is connected back to the input of the system to produce a new output. So the input for the system is actually contains two things or 2 types of inputs. I have what's called the external inputs of the system. Those are the external inputs. The system also have this connected feedback. We call it the internal input, or in other names we call it the feedback. Now, in order to realize the time dependency of the output, we have to go through steps. Okay? In the first step, how this circuit would work, I will assume that C in initially equals to 0. So this system, I will trigger it to work. It will actually add, for the full adder, will add 0 to A0 to B0. يبقى in step number 1, A0 will be added to B0 to 0. When I add A0 to B0 to 0, this will give me the output, will give me S0 and C1 from the definition of the addition from chapter 2. If I will get here S0 and I will get C1 in step number 1. Okay? Now, those are shift registers. That means the values of the registers here after step number 1 should be shifted down one step. So actually, shifting down means the bits will be displaced one step down inside those registers. Okay? So A0, B0 have been already lost. Enter the full adder and give me the answer. And right now I have A1, A and B1 applied on the adder. So right now in step number 2, this adder, this full adder will have the following inputs. It will have C1 from the feedback, it will have A1, it will have B1 added together. When you add A1 to B1 to C1 for the addition, this will give you the answer as S1 and C2. Again, this is a shift register. So S0 produced in the first step will be shifted down one step and will be replaced by S1 from step 2, and also the feedback here will change from C1 to C2. Agree? Now going to step number 3. In step number 3, A1 and B1 have been shifted already inside the full adder. So right now at the beginning of step number 3, I would have a new values applied on the inputs for my full adder. So right now I have C2 coming from the feedback, and since I already shifted those registers, I would have C2 from here, A2 and B2 added together. Step 3 will have A2 and B2 and C2 added together to give me S2 and C3. This shift register will shift the content of the output here one step down. So I would have here S2 produced and C3 produced. And those registers shifted the inputs one more step down. So right now at the beginning of step 4, I will have C3 coming from the feedback, A3 and B3 from the inputs. When in the beginning of step 4, I will have here the system is ready for step number 4. In step number 4, I'm adding A3 to B3 to C3, and this will automatically produce for me S4 and S3 and C4. This is a shift register, so it will shift down the results one step down. So I would have here S0, S1, S2, S3, and C4 produced, okay, by the circuit. Agree? Make sense? Can you see here the demonstration? So this new system is different from the system that we have built before. It's different in three regards. It has a memory to store the inputs and the outputs. It has a feedback, the output of the system connected to the input of the system. The output of the system is not fixed. It depends on an external inputs and the internal inputs to produce each time a different output. So the system is time dependent, have a storage or memory, and it has a feedback. If the system has these three characteristics, we call this a sequential circuit. So, and this is designed for what we call the serial adder. What is the advantage of this over what we already have built in chapter number 4? It is obvious, okay? There is nothing come for free. You are paying something to get something else. Here, the circuit is definitely simpler. Instead of having multiple full adders, I have only one full adder and I perform the operation. However, I have to add only memories, as you can see. So there is no need for designing or building more full adders. Only one full adder will do it. Second thing, which is the most important thing, is the scalability of the system. Right now, if you want to convert this from 4-bit adder to 8-bit adder, shall I add more logic, more brain? The brain here for this circuit is the full adder. Shall I add more brains? The answer is no. All what I have to add here is simply more memory. That's how our computers, our laptops, our digital systems nowadays work. You have only one microprocessor in the machine, in your laptop. And if new versions of software comes with larger memory footprint, are you throwing your laptop and bring another? No. If the memory, if a new software is coming, all what you have to do, you may add extra memory chips to allow more complex or more advanced programs to run on the same processor. So the brain is one, but the capacity of the memory is expanded in order to run new programs. Okay, which is the main advantage of the sequential circuits. Right. Do you pay something? Yes, I am paying. What I pay? First of all, definitely I am paying the cost of the memory, which is cheap. The second thing is that I am paying in the design delay. Because right now, as the example that we have shown here, when I give you a very simple operation, 2 multiplied by 3, I just give you the answer as 6 at once. But here, in order to perform this operation or that operation, I have to go through a sequence of steps through which the intermediate outputs are being produced. So that means the output will not be ready for me at once. It takes some time until the circuit responds and gives me the final answer. So since I'm doing the process sequentially into steps, I'm spending more time to actually produce my output, which is actually its cost. The cost here is time of the circuit response. Agree? Motivated enough? Now, our mission is to start building those circuits. In the chart that you can see here, in the design here, what is the new thing that you think that we have to learn to build in order to achieve that nice design? Full adder, we already did it. So we here want to learn how to build a memory, a storage, okay, which is the new thing. So our mission, our first mission in synchronous or sequential circuits in general is to build a memory or a storage. How can I build a storage? Building a storage from digital logic design circuits using the logic gates that we have already learned. We will not bring new components. We will not manufacture something new. Still, the logic gates that we have used through chapter 2 and 3, ANDs, ORs, inverters, NANDs, NORs, will be used to build the memory. So the engineers have started by building the first memory cell, and its design is very simple. And from the design you can recognize how simple it is, and it complies with the characteristics of what? Of the sequential circuits. The first memory cell is a very simple circuit that actually shown here, okay? And I just want to put some arrows to indicate the flow of signal. What's this? These are two inverters connected back to back, nothing else. From the drawing itself, you can easily recognize that this is a sequential circuit. Why it is sequential? The output of one of the inverters is connected to the input through the feedback to the input of the second inverter. The same thing, the output of this inverter connected to the feedback of the first inverter. And this circuit is called the 1-bit ROM. You know what's ROM? ROM stands for read only memory. ROM. Why it is ROM? Because you cannot write to that circuit. There is no external input. Do you still remember here we talked about the internal input connected to the feedback and the external input. For this circuit, there is no external input here that the user can change the stored value. So how will this act as a storage? At manufacturing time, if you originally have manufactured this and applied some logic 1 here at that input, this automatically means the inverter will change this input to 0, and this 0 is connected to the feedback of this inverter. That means here I have also the logic 0, and through this inverter the logic 0 will invert it back to 1. Without applying any input to the circuit, the 1s and the 0s will keep circulating inside the circuit forever. Okay? And the circuit without an input will give you an output. That's why we call it a read-only memory. And there is one characteristic that we have to indicate for those kind of synchronous or sequential circuits, which is that the output of the circuit, we will call it Q, and the circuit also produce for me the complement of the output, which we call it Q bar. The circuits always, it's some common known phenomena for those circuits. We call their outputs Q, and the circuit automatically should also produce for me the complement of the output Q bar. Okay, so this is the first ROM cell. It's storing the logic forever with no change, with no possibility for changing it. However, without applying anything, you are producing an output. Is this a sequential circuit? Yes, it's connected to the feedback. There is no time dependence here because the circuit's not changing, but I have at least value stored here forever. Okay? We are more interested on something like this, a RAM, some storage that I can change the stored value inside it. So how can I build a one bit of a memory that I can read, write, okay, from it? This is actually what we want to, or what we will explain inshallah in part number 2 of lecture 23. This is part number 1. We will stop here for a break and we will come back for part 2, through which we will modify this circuit in order to make it more usable for the end user, to allow the end user to read the content and also to write either value 0 or value 1 inside the memory cell. Thank you, and see you in part 2 of lecture 23 inshallah.